Before we discuss logarithms, let's review exponents. A few exponent rules you should know from previous years. A base raised to a negative exponent results in the reciprocal of the base raised to the positive exponent. So for example, 2 to the power of negative 3 results in 1 over 8. 8 is 2 to the power of 3. Raising a base to a fractional exponent results in radicals. A to the power of 1 over n results in the nth root of a. So for example, 8 raised to the power of 1/3 is the same as the cube root or third root of 8, which equals to 2. A raised to a fractional exponent with a numerator and a denominator results in 2 steps. The denominator takes the nth root of a, and the numerator is just a normal exponent. So for instance, 27 raised to the power of 2 over 3. First, I take the cube root of 27, which is 3, and square it, which would result in 9. On to logarithms. A logarithm is just taking the inverse of exponentiation. So first, some terminology. I have 2 raised to the power of 4 is 16. 2 is called the base, 4 is called the exponent, and the result when I raise 2 to the power of 4 is 16. This is a logarithm. Notice that the base has remained the same. The base when I take the exponent is the base when I take the logarithm. But now these have sort of swapped. I'm taking log base 2 of 16, and the result is the exponent. So all a logarithm is finding out the exponent that takes you from this base to this number, which we call the argument of the logarithm. Let's try some examples. We call this exponential form and this logarithmic form. These are equivalent. We can always rearrange this by saying this base raised to this exponent results in that value, or log base b of this number results in the exponent. Some examples. Log base 3 of 27. Ask yourself, what exponent takes me from this base to this number? Well, 3 to the power of 3 is 27. That's our answer, the exponent that solves that little equation. Log base 4 of 1 over 16. Notice I went from a whole number to a small fraction. That tells me that my result is negative. 4 raised to what exponent is 1 over 16? 4 raised to negative 2. I know that 4 squared is 16. Therefore, 4 to the negative 2 is the reciprocal 1 over 16. This is an identity of logarithms. Regardless of our base, log of 1 will always be 0. Anything raised to the power of 0 equals to 1. So for example, log base 5 of 1 is 0. 5 to the power of 0 is 1. And finally, log of 100. Notice I didn't write a base. We call this the common logarithm. If you don't see a base, the base is 10. So log of 100, we're asking ourselves, 10 raised to what exponent results in 100? The answer, of course, is 2. 10 to the power of 2 is 100. Sometimes, in order to evaluate logarithms, we're going to have to use some laws to simplify them. There are 3 laws of logarithms. The first one says, if I have log base b of some argument plus log base b of some other argument, same base, I can rewrite that as a single logarithm with the same base, but multiply the arguments, taking 2 logarithms and writing them as 1. There's also one for subtraction. Log base b of x minus log base b of y becomes log base b of x divided by y. 2 logarithms into 1. And lastly, this one will come in handy when we start solving exponential equations. This third property says that when you take log of something with an exponent, we can just drop the exponent down in front and turn it into multiplication. This says log base b of x times n, which used to be the exponent up here. So let's see how these can be useful when we're evaluating. This first example is base 6. If I try to evaluate log base 6 of 4, that's not a very nice number. It's a decimal number. Let's use the first law. Because this is addition and these have the same base, I may rewrite this as a single logarithm of base 6 with the arguments multiplied. Well, 4 times 9 becomes 36, and log base 6 of 36 is easy to evaluate. 6 to the power of 2 is 36, and the final answer is 2. Here's one with subtraction. Log base 5 of 75, once again, is not a nice whole number. Neither is log base 5 of 3. But because these have a common base, I may rewrite it as log base 5, the arguments divided, first one by the second one. Now that it's a single logarithm, this turns into just 25, and log base 5 of 25 is also very easy. 5 to the power of 2 is 25. My final answer is 2. The third one is useful when we're dealing with radicals. Log base 4 of the cube root of 16, well, that's not a very nice number. Let's rewrite the cube root of 16 as 16 to the power of 1 over 3. Now, using my third rule, I may simply drop that exponent down in front and rewrite it as multiplication, and evaluate log base 4 of 16, easy, 4 to the power of 2 is 16. I can replace this entire thing with a 2, and I'm left with 1/3 times 2, final answer, 2/3. We can also use the laws the other way. In this example, I have a single logarithm, and what I've done is I broke it apart into 2. This is not very nice. I don't want to deal with this number. Let's break this apart into log base 7 of 49 plus log base 7 of 7 to the 1/2, which we know is the same as the square root of 7. This was one argument, and I broke it apart into 2 logarithms with a common base. Now, each of these is much simpler to solve. Log base 7 of 49, I know that the exponent that takes me from here to here is 2. Using the third law, I simplified this, drop this down in front. Log base 7 of 7, fairly easy, 7 to the power of 1 is 7. Multiplying that by 1/2, 2 plus 1/2 is 2.5, or 5 over 2. Another way to use our laws is to take a long expression like this and rewrite it as a single logarithm. It may not look that much nicer, but we turn 3 logarithms into 1. So first things first, I need to get rid of these coefficients in front. I can use law 3 in the reverse by bringing this number back up as an exponent. So now I've got log base 5 of x squared, y cubed, z to the 4. Now I notice these all have a common base, which means I can use my first 2 laws. Here I'm adding, which means I can bring these together into a single logarithm of base 5, where I multiply the arguments, x squared times y cubed. And now I have to deal with this one. Again, common base and subtraction means I can rewrite this as a single logarithm, same base, this divided by this. I've turned one long expression into a slightly shorter one.